Okay, everybody. Good afternoon. How's it going? Okay. How did lab 1 go? Pretty good? Happiness? Everyone okay with the assignment due tonight? All right, good. Yeah, so hopefully it was a little bit of fun and you were able to write some MATLAB code, be able to see the importance of the time steps, and how it affects the Euler method, how it affects the Verlet velocity method, and then you're able to compare the two of them. And hopefully you've got a little bit of familiarity again with MATLAB, how to do the plotting, how to change the axes, and various things. Those skills will be useful as you progress through your final report, and also as we do a number of things with ANSYS, because there will be examples when we run the ANSYS software and we perform finite volume or finite element methods, where you want to take the results that ANSYS gives you and you want to be able to plot them. So don't think that MATLAB is completely going away. All right. Administratively, any questions? Yes.
So with the lab grading, we only really submit like those 2 questions. Is it just gonna be like 50% first question, 50% second question? Or like how does the breakdown of that work? Or?
So I mean, there will. So for the post lab, right? When you simply put in answer the questions, okay, what were the parameters they used? That's not going to be weighted as heavily as, okay, show me the graphs and everything, right? Okay, but I think you'll be content with the way that the TAs go about. But good question. Yeah. Other questions? Okay. Yes.
For the post lab, are we expected to like give it like a report, or like what I did was just like pictures and like a couple of sentences describing it.
That sounds great. That sounds great. Yes. Please do not on the simulation exercises. The expectation is that you can usually answer them within a couple pages. When we get a little bit further, there will probably be a few more plots that you put in, right? This is the first one, so yeah, it's probably the vernacular low-key-ish, low-keyest of them all. Okay, so see, I can't even do it. My kids laugh at me. All right, so today we're going to talk about how particles interact with walls. And we'll also talk a little bit about drag. At this point, when we were doing the orbital mechanics, these particles are unbounded. They can go wherever they want. We're discretizing time, and we're still discretizing time. But now we're going to introduce this idea that where you are matters. So where you are relative to a wall, gone through the wall, have you not gone through the wall, right? That dictates what's going to happen in the next time step. So today we'll talk about how these particles interact with hard walls and what we call periodic walls. And you'll get a little snippet of code that you can maybe think about in terms of pictorial diagrams in your head, and we probably won't go to the relevant research example. Really the question that we will be answering is, how do we model walls as our boundary conditions in particle dynamics. So if you drop a ball and it bounces back up, what are your realistic expectations of what you will observe? Or if you're playing racquetball and you hit a ball and it goes against the wall and it comes off, what are your realistic expectations? What do you think is going to happen? Yes?
The return distance will be shorter.
Okay, so yeah, so it's the ball in this case, if I'm dropping it, it's not going to come back to the original height. Okay. Why is that? Yes, your name is
Will.
Will, and your name is Cole. Cole, Will, John. Okay. Yes, Will.
When it bounces off, it loses some energy when it's redirected, whatever means.
Right, yeah. So there's going to be some of it's not a perfectly elastic collision in that case. The ball ends up heating up just a very slight amount, it absorbs some of the energy. Okay. What's another reason that it wouldn't come back all the way or bounce back and go all the way back toward you? So that's one reason. We have the inelasticity of the lossiness of the collision itself, and the other reason would be air resistance, right? Or drag. Okay? So those are kind of the two things that you can imagine leading to loss. We're going to assume for now, and pretty much through the course, that when a ball, because we're not going to talk about balls hitting walls forever, but when the ball hits the wall, it's going to behave elastically. Okay? It just makes it simpler. There's no reason why we can't adjust that. We can't introduce some loss function there, but right now, if it hits the wall, it's an elastic. It is an elastic, not an inelastic. It's an elastic collision. So that means that momentum and kinetic energy are going to be conserved. And if we draw the wall, but there's still the opportunity for loss. Okay, and like we said at the beginning, we're going to talk about drag. Okay, so you could imagine modifying drag somewhat appropriately to try to compensate for the losses in the wall based on what happens when it's in the air. But the physics are not exactly identical, and depending on how long you're running your simulations, you could have errors accumulating because you're making inappropriate assumptions about why the energy is being lost in the system. Well, the wall. Oops. Might look something like this, and we have a ball with some velocity, and we'll call that V1 coming in, and maybe it's hitting the wall, and it comes off, and the angle of incidence is supposed to be equal to the angle of reflection. Right, that's another assumption we're going to make here. We're also going to assume that my drawings stink. And this will have some velocity in that direction. So if we have a coordinate system that looks something like that, we can say that this incoming velocity has an x component and a y component, and in this case, v1x and v2 or v1x and v1y are aligned with the x and y coordinates, and when it comes off, we can say that it has a v2x and a v2y. Okay. If we say this is the j and this is the I direction. All right, what would we say here? We would say, well, the V1xi, right, is what we would be describing as going to the right here, and V2x, assuming that this magnitude, right, is positive, right, it would be going in the negative direction. Okay. And in terms of what's happening, the relationship between the y components, we just say that they're equal to each other. So that's what we expect in terms of what's happening with the velocity in these kind of simple elastic collisions. Now, we can also say that the magnitude of these two velocities is the same. Typically, we're going to be using pretty small time steps, okay? So here we've got a time step that's, you know, some distance away from the wall, and then at the next time step, we're about the same distance away from the wall as well. And as you can imagine, right, this particle is not losing mass, and this particle is the same particle, but V1 is at one time step and V2 is at another time step. So that helps us, you know, describe the velocity, but we also need to describe the position of that particle. Right? So where is it going to go? This angle of incidence has got to equal the angle of reflection. And then where does that put it? So we're going to talk about that. And as we talk about it, we're going to first, though, go into a little bit more of a definition of how we define a wall. Okay? So how do you define the wall? A hard wall. Well, we give it a location, and we prescribe a normal vector coming out of that. Right? In SolidWorks, you have multiple ways to define planes. Right? You could, I guess in geometry, you know, more appropriate, right? But you could somehow pick a point and then pick an angle. You could pick 3 points. You could pick something that is orthogonal to another plane, right? There are a number of ways you can define a plane. And these walls are essentially just planes. So what we're going to do is we're going to generally say, here is, I don't know, what would you use black? Here is a wall. And we'll pick some point on that wall relative to our coordinate system, and we'll define this position on the wall like so. So this will be a position vector for the location of that point on the wall. And then the other way we can define the wall or the plane is with a normal vector to that plane. Now, if we have a particle at one time step, and maybe at the next time step, it's over here. Okay, so we have two options for this wall. in reality, we know that the ball is not going to go through the wall. But in simulation, unless we have a conditional statement in place, it's going to go through the wall, right? The wall is not, we had to tell the computer, yes, you have traversed the wall, you have to now do something. So we need to know if we've crossed the wall or not. And how can we go about doing that? That's the question. Any ideas how you would go about doing this? Yes.
Since you know the position of the wall, you can correspond to the ball using the ball as like X position in the direction that you find is opposite of the ball.
Okay, yeah. So one way you could do it, at least in 2 dimensions, right? Or the way we define it, right? You've got an X and Y axis. You can say, hey, Y equals mx plus b, right? I remember this equation for a line, and I can test, right? If I plug in my X coordinate, right? Am I above or below the Y that I get, right? So if I have a Y equals mx plus b, that would be one way to do it. What's another way you can try to do it? Yes?
You can make like a domain of where the ball can maybe move, and then another domain where it can't.
Okay, right. So, yes, so you have, yes. So yes, so that's right. What we're trying to do is we're trying to figure out, okay, which domain it's in, right? Where the ball is not able to cross it, or the ball's not allowed to be in that region or not. Okay, yes, Parker.
Just a question, does the ball have a geometry or just a
This is a very good question. Thank you for asking that. What do you all think? It's a point mass, right? We're keeping things very simple. So there's no rotation, right, involved. Or I mean, it could be rotating, right? But we're not keeping track of any angular momentum for this problem. If it were a link on a robot, or if it were, I don't know, a rope with 2 masses on the end, right? That would be something that we're not capturing. Okay. We can model a remarkable number of physics. That's the way to put it, by using singular point balls and looking at how they interact with each other. And when we do molecular dynamics soon, you'll be able to kind of get an idea of how other larger macroscopic behavior might emerge just by the interaction of individual balls. But this is just a point. So as a location, as a velocity, and there could be fields on it that are going to induce some type of body forces to it, and acceleration. So this is the way that Professor Singer thinks about it, okay? And the way that your lab will think about it too, okay? We're going to go ahead and define, let's see which one, yeah, we can use this. We'll define a vector that describes the position of the ball at that time step, okay? When it's not through the wall, okay? And we'll go ahead and we'll define another vector when it's inside the wall, okay? And now we'll define vectors relative to the point location that we've described for the wall itself. Okay? So remember, this RW vector is what we've said is the location of the wall. And we can say that, let's see, we'll do this one. We can say that the distance from that location on the wall to the ball, or to the particle, is described by d1 there. And in this case, we can also describe the distance from the wall, that location on the wall, to that other ball that might be beyond on the other side. Okay. So you can kind of see here that, well, RW plus D1 is equal to R1, and you can also see that RW plus D2 is equal to R2. Okay. So, I don't know, it's kind of, we can write those out. And so using those parameters that we just defined, just the positions, okay, of the particle and the positions of the wall, we know that the D1 is going to be equal to the R1 minus the RW, and the D2 is equal to the R2 minus the RW. Okay. So if you're thinking, in my MATLAB script, I am keeping track, right, of where that satellite is in geosynchronous orbit, right? So R1, R2, R3, R4, R5, whatever. We're now, after the first lab, we're very good at knowing what R is, okay, as a function of time. And we didn't have any walls. Okay, but we've also now, if you define a wall this way, you know where that specified location on the wall might be. So now you can figure out these distance vectors. We haven't used the normal vector, right? That's the other piece of information we can use. So now, with these D1 and D2 vectors, how would you go about figuring out if you've crossed the wall? What would be an approach? Yes? Yes. Right. So we could use this D vector, right, dotted with the normal vector, and if that value happens to be greater than 0, okay, meaning that the angle between them is acute, then we say, okay, we haven't crossed the wall. If the angle is obtuse, this mouse is, okay, the angle is obtuse between D2 and the normal vector, then we can say that we've crossed the wall and we have to take some action. Okay. So that's the kind of the trick here that we can use. So if the D1 dotted with the normal vector is greater than 0, we have not crossed the wall, right? And in contrast, right, if the D2, or, you know, essentially it's a D, but we're saying D2 here, as it is, in fact, less than 0, we have crossed the wall. Okay. So this is kind of a nice little trick that Professor Singer likes to use, and this will now trigger a set of next steps if we've crossed the wall. So we've already kind of described what happens with the velocity. Okay. And so we can just write this out again now with kind of a slightly more angled wall. So in this case, you have a particle. It has some incoming velocity. We can call that v1. And it has these components. So this is going to be essentially the x component. But we can also think of it as a normal component. And we can also think of this over here as a parallel component of the incoming velocity. And I gotta stop writing 2. That's why. Okay. And so this would, come in like this. All right. And, we want to, instead it's got to bounce off. Like that. And it has a V2 coming off, like we said, and we could say that it has a V2 parallel, and we could say that it has a V1 normal. And the wall, of course, still has this normal vector. Okay, so here we've got V1 normal plus V1 parallel, which is going to give us our V1. Over here we have a V2 normal plus a V2 parallel, which gives us our V2. And if we're interested in knowing, okay, what is V1n equal to, right? So the V1n, well, maybe it's easier to do the parallel one first. Okay. That's a bummer. I think the battery might be going on this. Okay, so we have this V1 parallel is going to be just equal to or the V2 parallel is just going to be equal to the V1 parallel. And the V2 normal, okay, well, it's going to have the n hat direction, right? It's coming off. Like that. It's coming off like that. So that will be, so we could say, okay, it's something times that particular value, and we could just say, all right, it's essentially the magnitude of V1n times that. Okay. So that's kind of the same exact thing that we did at the beginning when we're thinking about it being an elastic collision. The position, though, is figuring that out is a little more complex. Okay, so once again, we define a wall and if we say that this is the position of the wall, and whatever, this is the x and the y coordinate, like that. We can begin to think of this position of a particle let's do a different color. After it's gone through the wall, and the position of the particle if it had gone through the wall. Okay, so the particle was, you know, like, let's say, that's what it's doing. In a time step, it would have come through to this location. Okay, so this is the location going after it's gone through the wall. So we'll say that this vector right here, we're going to call that RP through the wall. And this is the position after. Okay, like that. So we can call this one RP1 and RP2. And in this case, well, maybe we'll skip the P because the P can be a little bit confusing for parallel. So we'll just do like this, R1 and R2. Those are the positions of the particle. And we'll say that this is just R1 and this is R2, like that. Okay. We can divide the location of these or we can think about having these distance vectors again to these two locations. So here I can say this is a D1, or I can say that this is a D2, okay, of where we want to be. Okay. So the D1, okay, can be broken into two components here. It can be broken into a component that is parallel to the wall and also a component that's perpendicular to the wall. So this is the parallel component and this is the perpendicular component. We see that the D2 parallel to the wall right here, okay, along this, is going to be the same as the D1 parallel to the wall. So if we want, we can say that the D1 parallel is equal to D2 parallel. Okay, and how do we calculate out these these vectors? Well, if we know the first bit, right, we know this and we want to know this. Well, we can see that RW, this black line here, plus the D1 is equal to the R1, right? So R1 is equal to RW plus D1. Okay. We can also see that this the D1 plus, or the D1 parallel plus the D2 normal, okay, is equal to D1. Okay, so we'll say this is a D2 D1, I'm sorry, normal. Okay, and it's coming from this point into there, and this one, like we said, is a D1 parallel, like that. So one way to figure out where this new R2 is, this particle is to say, well, I know what my R1 is, I knew what my position there is, and I'm just going to subtract twice, or I'm going to add this D1 normal component twice so I get there, right? Because that D1 normal is the same, right, as the as you could say this D2, or its opposite, if you will, this D2, so we'll just say that D2 normal is equal to minus D1 normal. Okay. So we've kind of already, we've dictated that the D1 parallel, okay, is the same as the D2 parallel, right? Or the D2 parallel is the same as the D1 parallel. And we can also say that the D2 normal is equal to the minus D1 normal if we like, and that's how we can do that. Or we can also say that the position of R2 can be thought of as, I'm going to go RW plus D1, okay, minus 2 of these D1 normals. Okay, so this is another way to write it out. So R1 going along here plus the D1 minus this one minus it again gives me the R2. So minus 2 times D1 normal. Okay? So this is a complicated way, okay, to keep track of where that particle that has gone through the wall needs to end up in the next time step. And it's just saying, hey, angle of incidence is equal to angle of reflection, but we're doing it with vectors so that our MATLAB code or our iteration, our Euler or Relay method can keep track of where we need to be. Any questions on this? So, this is what it looks like in terms of MATLAB code. All right. So, first thing is we have a vector relative to the wall. Okay. So it's going to be the position minus the position relative to the wall. So that's giving us the dW. We do a dot of the dW and the normal vector. And if that is less than 0, then we have to proceed to change the position. Right? And you see there's no else in this conditional statement, because what it's doing is saying only if you cross the wall boundary do you need to change the position. Otherwise, just keep on marching through your normal code. And we can keep track of the number of bounces that we have, just for kicks. How can you have a ball hit a wall multiple times? Yes. Okay, sure. So you can have a second wall that bounces back in between. What's another way you can have multiple bounces? Yes.
If there's some sort of like gravity.
Right. So gravity could be acting, right? You drop the ball, hits it again, right? So anyway, so this is just a way to keep track of the bounce counters. We figure out what the normal velocity is. Okay, so this is for that next time step. We figure out what the parallel velocity is, which we've discussed. Okay, which we can think of as the velocity, in the next step minus that normal velocity. All right, and that normal velocity was dictated by calculating a dot product. We can figure out what the new overall velocity is. So we have the normal and the parallel. And then we can figure out, okay, where is our new kind of normal position and where is our new parallel position? Okay, and we can use the dot product of the dW vector and the normal vector. Okay? And we can figure out the parallel by using the dW minus the Rn. And then we can figure out, that's the parallel component, and then we can figure out where the new location is by doing Rp minus Rn plus Rw. Okay? So this is keeping track of what's happening as we've gone through the wall, and we're now resetting it, we're putting it back where it needs to be. One thing that's pretty important when you define a wall is which direction the normal is going to be going. So you're going to see in the lab that you have the opportunity to kind of define a wall by its angle and a position. Okay, so you're going to define a theta, and when you do that, okay, be careful and think about, okay, which direction is the normal coming? Because if you go through the wall, or if you're approaching the wall and the normal vector is in the same direction, right? You're just going to go through the wall and it's not going to notice, right? Because the dot product will be a positive. So it's very important that you have the vector pointing away from the wall, or you just have defined what the crossing means different, right? You could flip everything and say, okay, positive is when the dot product is positive when I've gone through a wall. And, I'm going to find my walls going with a vector in a wall direction, which is opposite to what we defined. Okay. All right, any questions? So, this part is how we define a wall, how we code the reflection off a wall in terms of velocity and position. Elastic collision. Let's talk now a little bit about what we call periodic boundary conditions. And so when let's see if this works.
So are you like a cow or a Dalmatian?
When I saw,
am That's a
this
spot.
movie, right?
It's not funny.
I thought.
Don't do
or
that.
I don't know what these are.
Miles' grades are pretty
Or
good.
by
A
recollection.
in AP Physics,
You can kind of see that
and a
as
B in Spanish.
character spot.
Mira,
He's
I gotta go. All right, bye.
he's lying to you. And I think you know it.
Okay. So we're going to be creating these types of periodic conditions, holes in the universe through which we come, and come back in a different spot. All right, so maybe it goes through here, and then maybe it comes out of one of these other holes. Okay. Now this is just my PowerPoint interpretation of what happens with periodic conditions. We have two walls. These are no longer hard walls with elastic collisions. These are now periodic walls. Okay? So, what we would expect in the past is you come in and you bounce back, right? That's what we've been doing. No. So the beauty of PowerPoint animation. Wow. All right. Let's do that again. Wow. All right. One more time. All right. Okay. So now, mathematically, how do you code this? Does this seem easier or harder than what we just did? What's that? Wait, okay, why?
Because you can just come up with like a different condition that it hits that wall, it just repeats the same code over again.
Right, it like sends it back over to the other side, right? Yeah, it's a lot easier from a coding perspective. In the space-time continuum, probably a little more difficult, okay? But at least in MATLAB, it's a little bit easier. We actually, though, we're going to use a function that allows us to do this. So let's say that, this is 0, and this is some length, and we'll call this 100 meters away. We know that if we go through, at least the way this is drawn, there it is, okay. The way this is drawn, right, this is vertical, and if we say this is X and Y, okay. When we get to this location, like when we go through there, what do we do with the Y? We just keep it, right? We're going to say the way this is all drawn, right, this portal over here, it's going to come out at the same Y location. So that's very easy. And what we're going to say here, when we get to 100, what we're going to say the X value is? 0, right? That's what's happening. Can you think of something that we use every day that resets itself twice? Yes. A clock, right? In the United States, we're using essentially 12-hour time, right? Not 24. And so maybe, in some of your math classes, they introduced the modulo function, right? Like, if you got to figure out, okay, 5 days from now is what day of the week and stuff, you're automatically doing the subtraction, right? And you're like, oh, if it's like 16, then I gotta do 2 times 7, then I get to 2, then I'm 2 more days along, right? That's what the modulo function does. All right, so if you're at 99 meters and I add 1, it gets me to 0. If I'm at 99 meters and I add 2, it gets me to 101. Minus 100 gives me to 1, right? So we can think of this periodic boundary condition as essentially being a modulo function. Okay, so So it turns out that this type of representation is useful, okay, even though it's a little bit more simplified in our case. And one example, okay, oops, repeated, is in research done by Professor Bacci in our department. Where are the periodic boundary conditions in this problem? Yes, Jonathan.
At the lower left and right corners?
Right. Okay. So what do you see there? You see that there's fluid flowing into the system with some blood cells in it, right? And then it goes through this network, this circulatory network, and it comes out, and it can go back in. Okay. And so this is a way to conserve volume and to have an infinite loop and a nice looking simulation. Okay. So there are situations where having periodic boundary conditions can be useful in physics if you don't want to spill, your guts all over the floor, right? You want to keep it back in. And our own bodies are like that. Heat exchangers, anyone use chillers, heaters, a radiator in your car, okay? Right? These are also circulatory systems where you're going to be introducing the liquid again. But the mathematical representation is pretty simple. Now, drag is the way, at least for this homework, that we're going to introduce energy loss and momentarily add some realism to what we're doing, and then we'll take it away for a nice, fun example. Okay, but drag is often given by this equation, where it's proportional to the velocity squared, and you have a coefficient, you have the density of the liquid, and you have an area. And then depending on what the profile looks like and what the wetted area might be, there are different definitions. When you're looking at an airfoil, that wetted area will be the span and the chord length, the product of them. If you're looking at the front of a car or something like that, or a sphere, then you would say, okay, it's the frontal cross-sectional area. So it depends on how it's defined. You have to be careful with that. But this is one way to calculate drag, and it's a very simple equation. And there are these correlations or these coefficients that you can use. When is it dangerous to rely on this equation at all? When we are dangerous. Well, I guess if you're designing something that has health safety involved, it could be dangerous. But what are the risks of just opening up a book and using this equation like it is? Yes, Jonathan.
Because it'd be like in the real world, we have wind and other factors.
Okay, yeah, so in the real world, you don't necessarily have this nice unidirectional flow, right? The air could be, or the air, or the water, or the liquid, or whatever it is, the fluid, right? It could be hitting it from different angles, okay? What else might be dangerous or risky? Yeah. Right, this was done with some perfect object, and there could be different surface roughness. The shape could be a little bit different. Yeah, there are issues there. Any other things? Yes?
Like stuff like that has to be like it's not gonna stay perfectly like that the entire way.
Okay, so that's an interesting point. We will talk a little bit about one-way fluid coupling and two-way fluid coupling a little bit later in the class. All right, so one-way, I should say one-way or two-way fluid structure interaction coupling. So usually, well, at least in this class, it's nice if you can assume that the object, the hard object, is not changing its shape, right? Because that means that, okay, the hard object is influencing the flow. And I don't want to think about the fact that the flow could be influencing the deformation on the object. Because then what happens? Oh, the object deforms. That means the next set of fluid particles that interact with it are going to see a different object. And that's going to mess things up. And then so in reality, yeah, sure, you know, the air particles are changing the shape of the airfoil on the plane. The most minuscule, like, you know, nanometer level stuff. So like with rigid structures, right, we don't worry about that coupling. But what happens when you lower the elastic modulus of the material, or the elasticity, or the viscoelastic properties of the material? That's when it gets tricky. So then you have to think, or you have the opportunity to try to think about this two-way interaction between the fluid deforming the object, and the object being deformed, which then interacts with more fluid, and they go back and forth. A simpler kind of observation here. Well, maybe it's not simpler, I shouldn't say that. This equation applies to steady state conditions. The fluid is going at a constant velocity. And in many cases, that's not true. Okay? So you lose some of the dynamic response. But if you're fortunate, I've used this equation or equations like it in the past. If you're going at small enough increments and changes in the velocity, and you don't have excessive turbulence, you can often assume that as you change your velocity in a slow fashion, that this drag force will scale appropriately. Okay, so you don't have to have that dynamic term. For those that are interested in, well, applying what you learned in your mass spring damper systems and differential equations, and using first and second order underdamped, or second order underdamped systems, or first order differential equations, what's problematic about using this relationship? Right, so if I have my good old mx double dot plus bx dot plus kx is equal to some forcing function, which term would you normally put the drag force on? In the mx double dot plus bx dot plus kx. Yes, Safa? The b, right? That's where you have, right, the k is the spring, the m is the inertia, and b is friction, or a loss of some sort. bx dot, bv. This drag term is v squared. Okay? So this also becomes problematic when you're trying to model simple dynamic systems, because in many cases the velocity is not squared. Friction's a pain in many cases, because when you're trying to come up with a closed form solution, because if I have Coulomb friction, right, then it's some static, then it's not proportional to this x dot, right? It's not going to be proportional to velocity. So then I have to come up with some other relationship. If it's v squared, then it's nonlinear also, and so I have not a nice closed form solution to write, so I have to solve it numerically. So you're going to use your ODE 23, ODE 45, and MATLAB to do these types of problems. There is one situation where it is okay to have a drag force proportional to the V. And this is for laminar flow. Okay, the Reynolds number is much, much less than 1. And it's about a sphere. Like that, right? And so in this case, the drag force is given by Stokes flow, about a sphere, and d is the diameter, v is the velocity of the liquid, and mu is the viscosity. So this is viscosity. with units of Pascal second. This is the diameter, has units of meters, and then this is velocity, which has units of meters per second. Okay. And so in this case, if you have very slow flow and it's nice and laminar, you can get a linear dependence on velocity. Okay. So for us, though, since we're doing numerics and we have balls kind of going through, right, we have these spheres, we can go ahead, assume that we're not dealing with a laminar flow case, and we can numerically calculate this drag. And so you'll get to do that in the lab. Okay. Now, let's look a little bit at some things that you'll see in the homework in the lab. How do I do this appropriately? Okay, that's good. Okay, so in one case, which you won't really do, this is a trivial case, but if you were to see this, okay, so the ball started up here, right? It had some initial velocity. What's going on here? One, do you think gravity's involved? Probably yes. Okay, and definitely yes. Okay, so we have gravity, but this is not, now you'll see that, okay, we're on Earth. We're like 100 meters off the surface of the Earth. Okay, it's hard to see that here, but, and maybe it would be nicer if maybe I should have been nicer, okay? But essentially, yeah, we're about 100 meters off the surface of the Earth. And so you do like the 6.371 or 6,371 kilometers, okay, is the radius of the Earth. And we're just above it. We're above it 100 meters. So that is captured in that little gap right there, okay? Here. Now, what about drag? Is drag active here? No, why? Why, Parker? Why is it not active? Why is it not drag?
Because it looks like the only force is
Okay, yeah, okay, okay, that could be. I need to give you a little bit more information, okay, to like analytically do this. That was my fault. Because I mean, it's hard to tell. Like I could have distorted this, but like, yeah, you are right that there's no drag. Okay, but what if I told you that the initial velocity was 50 meters per second?
which direction?
Huh?
Up or down or which direction?
To that direction. It started at 0 and it was in the x direction, the velocity was 50 meters per second. Yeah?
And you can analytically see that it took 30 seconds and it moved exactly 200 meters, so there's nothing going backwards.
Correct, right? So there's nothing keeping it from, there's nothing impeding its x velocity, right? So 50 meters per second times the 30 seconds, which is the time that we see at the top, that's 1,500 meters. Okay, so that's kind of a back of the envelope way to say, okay, there's no drag acting on the system. Okay. Is there a wall? Well, if there's a wall, we haven't hit it yet. Okay, it's just going. Okay, so let's add a little bit more complexity. Okay, so this simulation. Oh no, it's very embarrassing. What? Uh-oh. I'm in the wrong directory. Hold on, folks. Hold on. You may get to see. Or see, okay, so you can see this is classic. I have my gravity, but I don't have my drag function. So I have to go in. And I have to drag out my drag. Here should be, here's a drag function. So let's go back over here. There's the drag. Okay, now let's try. Okay. So this is a significantly more complex simulation. What do you see here? What is this? What kind of boundary conditions? What's going on? You know, with the physics. Just some observations. Yes.
The boundary condition seems to just to be like what the ground would be, so 0, and then it seems to be elastic because the parabola doesn't go straight back up in.
Okay. Okay. Right. So we're good. Good. Those are good observations. So one, the ground is at this 6,371 kilometers height. Okay, from the center of the Earth. Right. So that's one. Okay. And then you said there looks to be like there's some losses. I'm kind of summarizing, right? Now, we've only talked about how to do elastic collisions, right? So where does that mean that the losses are coming from? Because I didn't tell you how to do an elastic collision, an inelastic collision. I only taught you how to do an elastic collision.
Maybe other forces.
Right, so what's the other force that we just talked about? Drag. It's this drag, right? Okay, so what you're seeing, and you've nicely put together, we come down, well, let's look, maybe it's easier to look at it this way, right? The ball's coming in, and boom, boom, boom. It doesn't go as high as it did the previous one, and that gives you this idea, oh, well, there's a loss. And yeah, you know, if it was a real ball that's made out of rubber, there'd be some heat. The ball would be getting some heat, right? But in this case, we're modeling that loss in terms of the drag that we've added to the system. Yes, Safa.
Do you also have to consider like friction?
Okay, we are not doing that here, okay? But in reality, you might consider that, or you might consider as an inelastic collision. Okay. What's something else that's relevant to what we discussed today that this example has? And it's written in the title. Yes. Either one of you, whoever. Go ahead.
It's the periodic boundary.
Yeah, so it has a periodic boundary condition, right, at 180 meters. So when you watch it again, right, it came over here, it goes through the wall, right, and then it just stops. Okay. Now, we run this for 80 seconds. Will this ball ever reach zero velocity? In reality, would it reach zero velocity? Yes. Why in reality does it reach zero velocity? Yes.
Eventually the amount of force that's lost is greater than the amount of force to start with, so.
Yes. Right, and you remember that in your high school physics class, right, or in other physics class, right, you have this thing called Coulomb friction, right? And if you're below a certain threshold, you're done. You're static. It goes to static, right? You have dynamic friction, you have static friction, right? So that happens. In this case, we have this velocity squared term, but it's proportional to it, the drag that you have. So you'll get closer and closer and closer and closer and closer and closer to zero, but theoretically, you won't. Practically, though, the computer would eventually say, you know what, I can't keep track of all those digits anymore. And so it would round to 0, right? But you can see that you're just gonna keep slowing down over and over again. But that's not how the real world works. Okay? We usually do stop, and we're grateful that we do. Okay, so these are some of the fun things that you'll get to do with some slightly different numbers and conditions in the lab. Now, the post lab, okay, we'll jump to this, is what we call what I call pickleball and vacuum. Okay? All right, so why? Okay, so we'll do this again. This computer is just too fast. I should probably slow it down. Okay? The ball, okay, is starting at, let's do it again. It's just too fast. Okay, it starts here, and it has some initial velocity, comes down, hits a paddle around there, bounces over the net, hits another paddle here, and then goes back up. Okay, so what do you observe here in terms of losses? There aren't. And how in the world could you play pickleball with no losses, with no drag? In a vacuum. That's why I was so disappointed. It's like, this is too hard, and it won't go forever if I include drag. So I decided we had to pretend that we're doing pickleball on that. Okay. You're going to define the location of your paddles, okay, and these paddles are stationary. You don't have to change the angle, right? I mean, from what I've done here, okay? But you have to figure out, okay, 45 degrees is not bad. I'm not saying there's not another solution, but it's not a bad choice. Make sure you get the normal vectors right. Okay, so there'll be a theta rotation. We've been dealing with one wall. You're going to need to do with 2 walls. Okay, and then you can put them at different locations, which is part of what you're asked to do. Okay, and that is an interesting thing, right? Because if you move the walls over, if you move them to a different position, right, it may not exactly be where you want, where you think they are, right? Because you could be moving, or just be careful. I'll just say that. Okay, just be careful because you might just want to slide them this way, right? You don't necessarily want to slide them that way or this way, right? You just want to put them in this location, and then you can use a different velocity if you like as well, and a different time for these simulations. Okay, so these are just some applications that use gravity, use our elastic collisions with walls, use periodic conditions, although there's not any periodicity with this one, right? The periodicity comes from bouncing off the walls appropriately. Okay. Any questions? Thoughts? You know where you're going to be on Thursday, and that will be the lab, and then I'll see you all next week. Attendance coming.